I am Dr. Siddhartha Samanta, Assistant Professor of Health and Stroke Technology. Today, I discuss about very important topic of organic chemistry is infrared spectroscopy. Previous lecture, I already discussed about UV visible spectroscopy. This UV visible spectroscopy, from this UV visible spectroscopy, we understand what type of unsaturation are present. A molecule are unsaturated or not. Say this type of phenomena we understand from UV visible spectroscopy. In case of UV visible spectroscopy, energy absorbed, radiation, electromagnetic radiation absorbed in the UV visible region, and this UV visible region in the range of 200 to 800 nanometer region. And this 200 to 800 nanometer region, when a molecule absorbs some energy, some electronic transition takes place. That is, for electronic transition, we study UV visible spectroscopy, and the range of wavelength of radiation is 200 to 800 nanometer. But in case of IR spectroscopy, infrared spectroscopy, bond vibration, that is, molecules absorb some energy in the IR region, that is infrared region. Infrared region means this region 2.5 micrometer to 15 micrometer region. Is 2.5 micrometer to 15 micrometer region, and in that region, this is the 2.5 micrometer to 15 micrometer, that correspond to 4000 centimeter inverse to 667 centimeter. In that region, when some energy is absorbed by the molecule, and molecules, you know that molecules having some different type of bond. If a compound containing double bond, triple bond, single bond, and this bond is vibrate. Like you see that if we consider a bond is made by two atoms, one is A atom, another is B atom, and they are connected by a spring, and that type of spring, if this AB molecule, this type of molecule absorb energy, then this spring stretches like that way, it stretches, and it is close to each other, and in that form, in that vibration, it's absorbs some energy. And different type of functional group absorb different energy, and we get the spectrum. So basically, in IR spectroscopy, we understand about which type of functional group are present in a molecule. It may be aldehyde functional group, it may be carbonyl functional group, it may be type of functional group, maybe carboxylic acid functional group, maybe OH functional group. So when this type of functional group are present in a molecule, this molecule absorbs some energy in the range of IR region, and molecular vibrations take. So this type of spectroscopy also known as vibrational spectroscopy. What type of vibrational mode are active? That is fundamental mode of vibration. Fundamental mode of vibration, you see that fundamental mode of vibration is basically two types. One is bond stretching vibration, another is bond bending vibration. So stretching vibration, okay. So stretching vibration and bending vibration. That means stretching vibration, molecule stretching take place. That is like a spring, and if we stretch it like that way, stretching. and bending, this type of mode, bending mode. Okay. So stretching require more energy compared to bending. So stretching also two type. One is coupled stretching, another is isolated stretching. And bending is also two type, in plane bending and out of plane. So these are the several type of bending mode, stretching mode are present. In case of OH functional group, only two atom, one is oxygen atom, another is hydrogen atom. So in that case, isolated stretching take place. In that case, isolated stretching take place. Here you see that one is oxygen atom, another is hydrogen atom. So these are the stretch like that way. So this is called isolated stretch. And when stretching takes place more than two atoms, like NH2 group, so this type of stretching takes place. And this stretching is coupled stretching are also two types. One is symmetrical stretching, another is asymmetrical. For symmetrical stretching is two atoms far away from the central atom or close to central atom. So this type of stretching is called is symmetrical stretching. And in case of asymmetrical stretching mode, one atom close to central atom and another far away from central. So this stretching is called asymmetric stretching. Generally, asymmetric stretching is require more energy compared to symmetrical stretching. So these are the coupled stretching. And bending mode also two types. One is in plane bending and out of plane. In plane bending also two types. One is scissoring, another is rocking. You see that this is scissoring, and in case of these two atoms is same side. Movement of hydrogen atom is same side, and they are close to each other and far away from each other. This is called scissoring, and this is called rocking. Okay, so this is in plane bonding. Here all the atom, carbon, hydrogen, all the atom present in a plane, same plane. Okay, so this vibration is known as in plane vibration, in plane bending mode. And out of plane bending mode also two type. One is wagging, another is twist. When two atoms are up the plane and down the plane, up, down, in that way. So this is called wagging. And if two atoms, one is up, another is down, one is up, another is down, this type of bending mode is called twisting. So when a molecule absorbs some radiation, some IR radiation, that is electromagnetic radiation, such type of radiation, in the vibration mode is 667 to 4000 centimeter inverse in that region. So when this molecule absorbs the radiation, electromagnetic radiation in that region, the molecular vibration takes place, molecular stretching takes place, molecular bending takes place. Okay, and we get the spectrum. Now, which type of compound is IR active? What is the selection? Centrosymmetric molecule are IR inactive. That is, the molecules having permanent dipole moment is zero, IR inactive. And if compound having some permanent dipole moment, this type of compound is IR. Okay. Now, which type of molecule is IR inactive? Like H2, O2, N2, this type of homonuclear diatomic molecule. This type of molecules in any mode, you see that in any mode, any vibrational mode, the magnetic moment is zero. So this is the IR inactive molecule. But in case of NO molecules, CO molecule, this have some permanent dipole moment, and so it is IR active molecule. So during vibration, if molecule acquire some dipole moment, and if compound having permanent dipole moment, they are IR active. Now, carbon dioxide molecule is either active or inactive. If we see that the permanent dipole moment of carbon dioxide is zero, so it is basically either inactive. But in what mode? If symmetrical stretching mode, if we see that symmetrical stretching mode, in that mode mu is equal to 0, and we get permanent dipole moment is equal to 0, mu is equal to 0 in symmetrical stretching mode. So in that mode it is higher. But asymmetrical stretching mode, it is higher active. So during vibration, if a molecule having some dipole moment, then this molecule is also higher. Okay. Now in that IR spectroscopy, when a molecule absorbs radiation, then it's have some vibrational mode. Now, what type of energy it is? What is the range? Like you see that if we consider CH, CH molecule, carbon and hydrogen, and if we consider carbon, if we consider carbon halogen, so they are absorb same energy or not? Now, this type of bond are different, so its absorb energy also. So in that situation, Hooke's state a law. And according to Hooke's law, it is stated that according to Hooke's law, vibrational frequency is directly proportional to force constant K. That is square root of, obviously, nu is proportional to root of K. Okay. So it's directly proportional square root of force constant and inversely proportional to reduce. So vibrational frequency nu is inversely proportional to reduce. This is the mathematical equation of Hooke's law. Where mu is reduced mass is equal to m1 m2 by m1 plus m2. And this is the relation, mu is equal to proportional to root over of k by. So from this is very important law, Hooke's law in IR. From this Hooke's law, we discuss about which type of stretching takes place, what is the energy absorbed during this stretching. So there is some fundamental data, absorption frequency of some functional group. Here we see that NH stretching, OH stretching in the range of 3000 to 3500 centimeter inverse in that region. And in case of CH, 3000 to 3100 centimeter inverse. But CO, carbonyl stretching in the region of 1715 to 1730 centimeter. Like CC double bond, CC triple bond, CC single bond in that region. 1650 to 1650 centimeter. And after that, there is some bending. So, stretching requires high energy compared to bending. Arrange the stretching frequency. CC single bond, CC double bond, and CC triple bond. So we know from the Hooke's law, stretching frequency is directly proportional to square root of force constant. In case of triple bond, this bond strength is more. 1 sigma and 2 pi bond is more stronger. So force constant value also more, and it's require high energy for its vibration, its stretching. Okay. But if we consider CH bond, CC bond, and CO bond, the stretching frequency also depend upon the inversely proportional to the reduce, square root of reduce. For CAs, it's having reduced mass less compared to CO. So CAs is stretching frequency is more compared to CC and compared to CO. So this is basically the stretching how it is depend upon force constant K and the reduced mass. Hydrogen bonding also decreases the stretching frequency. If a compound having some hydrogen bonding interaction, so hydrogen bonding reduces stretching frequency. So generally CO carbonyl stretching frequency in the range of 1720 centimeter inverse. But for para-hydroxybenzoic acid, after hydrogen bonding, that is intermolecular hydrogen bonding, CO stretching frequency reduced to 1678 centimeters. Okay, and OH carboxylic acid OH functional group. This OH functional group appear in the range of 3500 centimeter inverse. But due to hydrogen bonding interaction, it's appear 2700 centimeter inverse to 2500. So after hydrogen bonding, this absorption band is brought in. And from IR spectra, we also understand, we also differentiate what type of hydrogen bonding it is. It is intramolecular hydrogen bonding or intermolecular hydrogen. If a compound having intermolecular hydrogen bonding, if we dilute it, then this hydrogen bonding breaks and its OH stretching frequency is increased to 3500. So it also IS could also differentiate which type of hydrogen bonding takes place. It is intramolecular hydrogen bonding or intermolecular hydrogen. For intramolecular hydrogen bonding after dilution there is no change. But intermolecular hydrogen bonding, OH stretching frequency, CO stretching frequency is increased. And what is the effect of CO stretching frequency if we attach some electron donating group, if we attach some electron withdrawing? So plus I effect group decreases CO stretching frequency. It is converted C double bond O to C single bond O, that is in that form. Okay. So CO stretching frequency is reduced by presence of plus I effect, whereas minus I effect group increases CO stretching frequency. If we attach some fluorine atom, CF3 fluorine atom, it increases 720 to 769 centimeter inverse. So minus I effect group increases CO stretching frequency, whereas plus I effect group decreases CO stretching. So electron donating group reduce the CO stretching. Now, what is the effect of conjugation? Conjugation effect, if we see that a carbonyl compound is conjugated with a double bond or with benzene ring, this conjugation, due to this conjugation, this carbonyl stretching frequency is reduced. Now, due to resonance, its CO double bond is converted somehow CO single bond. Here you see that benzene is directly attached with this carbonyl carbon, and so by resonance, its stretching frequency is reduced to 1648 centimeter. But in that case, there is a sp3 carbon are present. So in that CO stretching frequency do not affected by this conjugation by this benzene. So conjugation effect is reduced CO stretching frequency. So this is the conjugation effect. And ring effect. Here we see that three-member ring, cyclopropane, cyclopropanone. Okay, cyclopropanone, three-member ring. This is the four-member ring, five-member ring, and this is the six-member. So ring size, if we reduce ring size, CO stretching frequency also. due to more S character. This CO bond double bond is more S character. So ring size increase your stretching frequency. A small ring size, yeah, if the ring size is very small, then your stretching frequency also more. Now, what is fingerprint region? Fingerprint region, the region where the bending mode is present. That region is basically 650 centimeter inverse to 1300 centimeter inverse. In that region, we know that this region is fingerprint region. Why this type of this region is fingerprint region? Now, basically, we understand what type of compound are present. This region is important for identifying compound because the pattern of this region, that is spectral pattern, uh, for a compound is unique. Okay, so in that region, CCl, CO, CN, CC bending mode is present, and for a particular compound, this pattern is unique. So from this fingerprint region, we understand what is the compound activity. So this is the basically IR spectroscopy. From this IR spectroscopy, what is the application from this IR spectroscopy is used to identify chemical compound by matching their spectra to a database. IR spectroscopy can help establish the structure of an unknown compound. It is also help to measure the degree of polymerization. So this is the spectra, IR spectra. We already discussed about this IR spectra. From this IR spectra, we understand what type of functional group are present in the molecule. Eh? So this is the basic concept of IR spectroscopy.